It's a pleasure this morning to welcome Stephen Hawking. Of course, as you all know, Stephen discovered this wonderful paradox 40 years ago that has frustrated us, and this week clearly is frustrating us as much as ever. Hopefully, maybe he will dispel our confusions. In any case, the framework will be Stephen will give his talk, then we'll take questions, and then we'll prepare answers offline while we can discuss other things. So, Stephen.
Can you hear me? I am glad that I can join you all remotely from Cambridge for this program on firewalls. Some time ago, I wrote a paper that started a controversy that has lasted until the present day. In the paper, I pointed out that if there were an event horizon, the outgoing state would be mixed. If the black hole evaporated completely without leaving a remnant, as most people believe, and would be required by CPT, one would have a transition from an initial pure state to a mixed final state, and a loss of unitarity. On the other hand, the ADS-CFT correspondence indicates that the evaporating black hole is dual to a unitary conformal field theory on the boundary of ADS. This is the information paradox. Recently, there has been renewed interest in the information paradox. It has been suggested that the most conservative resolution of the information paradox would be that an infalling observer would encounter a firewall of outgoing radiation at the horizon. There are several objections to the firewall proposal. First, if the firewall were located at the event horizon, the position of the event horizon is not locally determined, but is a function of the future of the spacetime. Another objection is that calculations of the regularized energy-momentum tensor of matter fields are regular on the extended Schwarzschild background in the Hartle-Hawkings state. The outgoing radiating unruh state differs from the Hartle-Hawkings state in that it has no incoming radiation at infinity. To get the energy-momentum tensor in the unruh state, one therefore has to subtract the energy-momentum tensor of the ingoing radiation from the energy-momentum in the Hartle-Hawkings state. The energy-momentum tensor of the ingoing radiation is singular on the past horizon, but is regular on the future horizon. Thus the energy-momentum tensor is regular on the horizon in the unruh state. So no firewalls. For a third objection to firewalls, I shall assume that if firewalls form around black holes in asymptotically flat space, then they should also form around black holes in asymptotically anti-de Sitter space, for very small lambda. One would expect that quantum gravity should be CPT invariant. Consider a Gedanken experiment, in which Lorentzian asymptotically anti-de Sitter space has matter fields excited in certain modes. This is like the old discussions of a black hole in a box. Nonlinearities in the coupled matter and gravitational field equations will lead to the formation of a black hole. If the mass of the asymptotically anti-de Sitter space is above the Hawking page mass, a black hole with radiation will be the most common configuration. If the space is below that mass, the most likely configuration is pure radiation. Whether or not the mass of the anti-de Sitter space is above the Hawking page mass, the space will occasionally change to the other configuration. That is, the black hole above the Hawking page mass will occasionally evaporate to pure radiation, or pure radiation will condense into a black hole. By CPT, the time reverse will be the CP conjugate. This shows that, in this situation, the evaporation of a black hole is the time reverse of its formation, modulo Cp, though the conventional descriptions are very different. Thus, if one assumes quantum gravity is CPT invariant, one rules out remnants, event horizons, and firewalls. Further evidence against firewalls comes from considering asymptotically Andy de Sitter to the metrics that fit in an S1 cross S2 boundary at infinity. There are two such metrics, periodically identified Andy de Sitter space and Schwarzschild Andy de Sitter. Only periodically identified Andy de Sitter space contributes to the boundary-to-boundary correlation functions, because the correlation functions from the Schwarzschild Andy de Sitter metric decay exponentially with real time. I take this as indicating that the topologically trivial, periodically identified Andy de Sitter metric is the metric that interpolates between collapse to a black hole and evaporation. There would be no event horizons and no firewalls. The no-hair theorems imply that in a gravitational collapse, the space outside the event horizon will approach the metric of a Kerr solution. However, inside the event horizon, the metric and matter fields will be classically chaotic. It is the approximation of this chaotic metric by a smooth Kerr metric that is responsible for the information loss in gravitational collapse. The chaotic collapsed object will radiate deterministically, but chaotically. It will be like weather forecasting on Earth. That is unitary, but chaotic, so there is effective information loss. One can't predict the weather more than a few days in advance. In summary, it has been suggested that the resolution of the information paradox for evaporating black holes is that the holes are surrounded by firewalls, bolts of outgoing radiation that would destroy any infalling observer. Such firewalls would break the CPT invariance of quantum gravity and seem to be ruled out on other grounds. A different resolution of the paradox is proposed, namely that gravitational collapse produces apparent horizons, but no event horizons behind which information is lost. This proposal is supported by ADS-CFT, and is the only resolution of the paradox compatible with CPT. The collapse to form a black hole will in general be chaotic, and the dual CFT on the boundary of ADS will be turbulent. Thus, like weather forecasting on Earth, information will effectively be lost, although there would be no loss of unitarity. Thank you.
Thank you, Stephen. I haven't absorbed that yet, but would anyone like to ask a question or make a comment? Samir, yes, please. There's only one microphone.
Hello, Stephen. Thank you for that very nice talk. I was just curious about how one would actually get the chaotic structure just inside the horizon that you talked about, because if we follow the collapse in the normal expectations of gravity, the region inside the horizon also soon flushes out, and all the states there settle down towards the vacuum. That has been the reason that the information paradox has been so strong all these years. I would also like to add that we do have a construction, the fuzzball construction, which actually gives us structure just outside the horizon. Would you consider that structure as an example of the chaotic structure that you are looking for? And in case we don't assume that structure, how would we actually avoid just getting the vacuum at the horizon?
That was Samir Mather, and actually Stephen had asked that questions be repeated. That was a lot to repeat, so that do you need that to be repeated, Stephen?
No.
I think many of us were wondering the same thing, but perhaps are there other comments or questions for Stephen? Okay, this is Jim Hartle.
Hi, Stephen. How would the chaotic nature of the collapse you're proposing...
We can't hear you, Jim.
Beg pardon?
We can't hear you.
Closer. How would the chaotic nature of the collapse you're discussing, what would the signature of that be in the dual field theory? So I'm repeating it. The chaotic nature of the collapse you're proposing, what would the signature of that be in the dual field theory?
It will probably take Stephen some time to answer the questions, of course, but if there's any additional issues people want to raise before we let him respond. The war continues. This is Lenny Susskind.
This time I think Stephen and I are in the same army.
Oh, we can't. Sorry, we can't hear you very well. If you could hold the microphone closer.
Can you hear me now?
Yes, that's better.
Yes. Well, I completely agree with you, Stephen, completely. But we still have to figure out what mistake AMPS made. So, at a technical level, the question is, what error are they making? What detailed error are they making? And some of us can't quite figure it out. So, the mic is off?
No, we heard that.
Now can you hear me?
We heard it, yeah.
Oh, you heard that. Okay, well, that's it.
Okay, this is now, so Lenny's question, what is AMP's mistake? And now Gary Hollis, this should be the last question I think we take.
Okay, well, I was just thinking maybe we could ask Don or Joe, if there is no actual event horizon, but there's an apparent horizon, would you guys say that there's still a firewall? Because, I mean, we've had discussions, if you throw matter in long after the original black hole's been around forever, you were saying that there would still be a firewall at where the original horizon was thought to be. So that sounded like you think there's a firewall just at the apparent horizon. Okay, so Gary asked Joe or I to give an answer. My answer is that what I think we have assumed is what I would call an adiabatic horizon. We've assumed that the space-time is evolving slowly enough that we can approximate the system by a static or stationary black hole. And in that case, the phenomenon happens at very close to the location of the event horizon of that approximating black hole. So we have not identified if there was some more dynamical process happening. We haven't done an analysis. Okay? But we're using something which, as I say, in the adiabatic approximation would coincide with an event horizon. It is also, therefore, a natural apparent horizon, a natural quantum. And that's where the phenomenon is coming.
Okay, so let's thank Stephen again. Okay, so Stephen, we will wait for your responses. Thank you. No, I was just wondering because this, Stephen introduced this notion that maybe this chaotic collapse could be an important ingredient in the black hole information puzzle, and that sounds very interesting in light of recent calculations of seeing turbulent behavior in ADS-CFT. There's always this like conflict between the fact that in the boundary field theory, if you get it from long-range approximation, you expect it to be sort of hydrodynamic and sort of generic feature of all turbulent flows, and yet in the bulk theory it's described by black holes, and I always thought that if you compare to black holes, things are more or less become exponentially because it's like a more linear. But there's been some recent work by Hong Li and people at MIT and others which have shown that if you actually do the calculation nonlinearly of perturbations of black holes, you see behavior very similar to turbulent behavior in the dual field theory. So, of course, that assumes a black hole, and Stephen is arguing that it's not going to be a horizon, so it's not really going to be a black hole. But at least that ingredient of behavior and turbulent behavior is being seen. Still have exponential decay due to quasi-normal mode range.
I think for that behavior it's necessary that the system is bigger than the thermal wavelength. So there are hydrodynamic modes and all that turbulent behavior.
I just want to remind people that one real problem is that semi-classically, information, vacuum matter, etc., sails into the center of the black hole, and semi-classically we have no understanding of how the information transfers to physics, considerations of how space-time works, how the information transfers. Transfers to outside the horizon, and this being chaotic is not the social way that it's clear that question is addressed. What's wrong with this MFS?
I just wanted to make a request to the room. Did anyone here understand Stephen's argument for why CPT symmetry and the symmetry between the formation and evaporation of black holes in thermal equilibrium implies that there can't be a firewall? And, could that person maybe, explain it?
Aaron.
So I think the argument goes something like this. You have a box of thermal radiation which is favored, but you imagine that there's a thermodynamic fluctuation that happens to produce a black hole. So this hole appears, it grows to a maximum size, and then it evaporates again. If this were a normal thermodynamic object, the way you'd analyze it is you'd start at the moment of time symmetry. You'd say that's the, whatever is the lowest the entropy gets. You start there, and then you have entropy increase either to the future or to the past from that moment of time symmetry. However, the difficulty is that if you think about this semi-classically, you would expect, you don't know whether it's a black hole or a white hole. So you could say, well, maybe it's a really tiny black hole that grows and then shrinks. Or maybe it's a really tiny white hole that unevaporates and then uncollapses. And the Penrose diagrams are very different from each other. It's really hard to figure out a consistent way that could be both a past and a future horizon. So you say, wait, is it 50% chance of one and 50% chance of the other? So my understanding is that what Stephen is proposing is that sort of because there's no horizon, so it's sort of neither. It's not really a black hole or a white hole. It's just a hole. And the one thing I'd like to add for myself is that I'm not convinced that's actually the opposite of firewalls. In my view, if there's a firewall right at the horizon of Planckian radiation, that might destroy any sort of semi-classical picture behind the horizon. So if you think of the firewall as being a sort of edge of space, and there is nothing behind the horizon, then I think that's consistent with it being neither a black nor a white hole. So I'm not sure that's really the opposite of firewalls.
Did you want to continue on CPT?
Yeah. I just wanted to make an obvious comment, which is that there are what you might call firewalls whose dynamics we understand. That is, in the formation process, you send in an agent who's going to, explode a bomb of radiation that goes up toward the horizon. So whatever your theory is, it has to at least include the possibility of that dynamics, which we already do understand, which, of course, is very special, but which can produce this kind of effect. I think what AMPS is saying is that there's some mysterious dynamics beyond what we've analyzed so far, which also produces such effects. But in any case, general arguments need to allow for this, obvious possibility of such radiation.
I don't think you produce anything that bad.
You can certainly produce something that's way above the vacuum.
I think a firewall is a lot worse than anything you'd ever produce that way.
I just wanted to comment on Steve Giddings' argument. Indeed, if you put anything classical at the horizon, and that's the mistake that people have been doing for ages, of course it falls in. If you cannot have anybody to keep it there. However, in string theory, we know that you have non-abelian effects, you have topology, you have stuff which actually can hover at the horizon scale. So I think one of the problems about not being able to find structure at the horizon is that people are not looking in the right place. People keep on looking at gases of gravitons and gravitational waves. Those are going to fall in, whatever you do. You need some other stuff, and string theory provides it. We know many examples where string theory has non-abelian degrees of freedom, has brane polarization, has topology, which comes in and works on a large scale without collapsing. And that's exactly what we have been using over the past 10 years to put structure at the horizon. And I think that's the only thing which string theory has. Maybe some other theories have other stuff, but as string theories, maybe we should use it first.
Actually, I'd like to respond. Are there examples of things which actually hover? You have, it looks like a Schwarzschild geometry right till very close to the horizon, and then there are things that hover. Are there examples like that?
There is
his word, hover, meaning that they don't collapse, meaning that you have a solution which is Schwarzschild to good approximation right to some microscopic distance above the would-be horizon, and that's stable.
So we can do near extreme black holes, which have the same Penrose diagram as Schwarzschild plus one electron. If you put Schwarzschild and one electron, you have the same Penrose diagram.
It's not really a conformal question. It's a question that has scales in it.
Yes, but the point is, if we can find in one Penrose diagram that you can have structure which hovers at the outer horizon, and that's something which we already have.
Well, I'm sorry, physics has scales as well as conformal structure. So I asked the question about a microscopic distance above the Schwarzschild horizon.
The Schwarzschild, there are some topologies, there are some black hole solitons, but they are very few and very unstable. So.
Yes, if you look at a little box just above the horizon, you will discover that there's some heat and some temperature and some stuff and some particles there, and you will always find it. So it doesn't go away, it doesn't fall in. It's called the Unruh radiation. I know, but that's just the way it is.
Okay, that's.
Well, another thing that Stephen said was that there may not be an event horizon form at all. I think that's an interesting thing to consider because, I mean, the event horizon, after all, is a very classical concept. I don't know how to define an event horizon in a real quantum gravity theory. So, and in fact, people like Abe Ashtekar and Martin Bojewald and Martin Bojewald, have made the point that because there's a singularity inside the black hole where we know semi-classical ideas break down, and because the event horizon requires global causal relations between, distant regions of space-time, event horizon is not defined. I mean, if you sort of try to imagine a space-time and you sort of remove the region around the singularity because you know it's not semi-classical, then we don't really know causal relations between points inside and outside. So there's a very real sense in which the event horizon may not exist. It may not be well defined.
I just wanted to respond to what Joe said and also what Gary said, just to put those two things together. I think what we are learning from the kind of things that Joseph just mentioned is that indeed the issue with black holes always has been for a short-shell black hole. If you keep something just outside the horizon, it has a great desire to fall in. So how do you keep something there? But what we have found is a qualitative picture which we extrapolate from simpler near-extremal cases. And I think that picture is what is interesting to us right now. And the picture is the following. If you have a compact circle in space-time, you can make it pinch off before you reach the horizon. And now this structure doesn't have the same problem that it is actually, there's something there to fall in. So it's not like you have a horizon and something hanging on outside. You come and you pinch off the compact circle, so there is no more space-time. And so just as Gary was saying, once you have a horizon, I don't know how to beat the no-head theorem. I think you can't beat it. Everything will fall in. But this mechanism which we actually find for much simpler states, if you ask me to guess, I would say we'd also hold for the short-shelled hole, though we don't have the actual constructions. But if you imagine compact dimensions pinching off, it's a very different way to put structure at the horizon. And I have faith that this is how things actually work out.
Yeah, I've actually believed since sometime in the 1980s when Lenny taught me this, that there really was no such thing as an event horizon. And black holes are formed by scattering particles in Minkowski space, and then they evaporate, and eventually particles come out. But I think there is an issue that Don brought up in his talk, which is not addressed by saying this. And that's simply the following. There's an issue of what the black hole entropy consists of. What are the states? And as Don said very clearly, we understand that in ADS-CFT. We think we understand it in the accelerated frame. If you listen to my talk next week, I will claim that the conventional understanding in the accelerated frame is wrong. But in the frame of the freely falling observer, there's only one state of low energy in quantum field theory, and we cannot understand the entropy in that frame. And I think, as Don said, that's a very critical problem, and that's there whether or not you believe there's an event horizon. And I'm going to propose a resolution to that, which everybody will feel very uncomfortable with. But I think this is an issue that has to be addressed, whether or not one believes there's an event horizon.
Well, what about buoyancy? Since Bob is sitting right here, and I mean, we're talking about objects can't hover in front of the event horizon, but you guys showed that they can, right? You carefully put them at the right radius, and in a buoyant force, they sit there.
If you have a zero mass or negative mass object, it can do that. I mean, you need to fill up have a box that is emptier. You need in flat space-time terms, you need a piece of the Rindler vacuum which has negative energy inside your box. And if you pushed your empty box in far enough, it will have negative energy. I mean, I think you can't do that. Is another way of getting at the point that I'm making.
So I have a dumb question about that. Bubble nucleation, late times, asymptote to that. So, like a Witten bubble asymptotes to that, even an ordinary Coulomb-de-Luce bubble asymptotes to something that's
Can you speak louder?
flying out at a light-like, on a light-like trajectory.
So,
yeah, if you have some sort of false vacuum decay, how does that fit into this no-go theorem? So that is, in some sense, a zero mass object.
Actually, string theory has orientifolds. Why are those not good negative tension objects to hover above the horizon? Orientifolds. They have negative mass, they have negative charge. Why can they hover above the horizon? String theory has objects which actually do exactly what Bob wants.
I think I was.
Joseph, I mean, orientifolds have negative energy, but I mean, what keeps the well. They only have half a space, right? You can only have one of them, and even then you only have half a space left, so they aren't really objects. Yeah. I mean, maybe Don, do you want to say something more coherent?
I'm going to correct something that I think Bob inadvertently said. I think he correctly said you need zero mass objects to hover above the horizon. You sort of said something about zero or negative, and your point was if you had negative mass things, you can combine it with a positive mass thing to make a zero mass thing. If the object is actually negative mass, it doesn't float. Negative mass things in GR follow geodesics just like any positive mass thing, and they fall in too. They're gravitationally repulsive to everything negative or positive, but they follow the same geodesics as something else as a consequence of the equivalence principle.
Okay, here is a model of fastball. So you just take the usual Rindler vacuum, right? Or no, not Rindler vacuum, sorry. The usual Unruh state, right? And you call all the particles and thermal excitations there the KK monopoles, okay? So this is a model of a fastball. And then you will have, I think, the same problem. So everywhere where the AMPS talks about measuring modes outside the horizon, okay, replace measuring mode by measuring KK monopole, okay, same story. And then if you say that there is something like complementarity where you can get into the interior, you might have the same issues. You'll have to. So I don't think it is changing the game fundamentally.
Yeah, I think it's very important to understand that that is actually not the structure of the fuzzball. The structure is actually the following. You have your Rindler quanta or the Hawking radiation near the horizon. That's fine, that's still there. As you follow it closer to the horizon, the theory is non-linear, so they start interacting. So you can ask, what do they do when they start interacting? And when they start interacting, it turns out that something interesting happens. The nonlinear structure they produce creates a completely smooth end to space-time. Recognizing that that is what the nonlinear structure actually does, I think is the crucial part.
I say that there are no event horizons, but only apparent horizons. And that a black hole is a metastable bound state. If black holes evaporate, there can be no event horizon, as many of you assume.
I'm a little confused about this hovering issue. I don't think anything hovers above the horizon.
Sorry, we can't hear you very well.
I don't know who I'm speaking to. No, I'm not. I agree with that. Well, you know, stuff comes in and stuff goes out. That's all. Okay, but still, there's a long period of time when there's something like a horizon, and we have to understand it better, as Tom said, what its degrees of freedom are. But with respect to this business of hovering, Nothing hovers above the horizon. Stuff gets ejected and it falls back in. It gets ejected and it falls back in. It's called the Unruh radiation, and it really is nothing in Minkowski space. It's just the vacuum fluctuations. Things fluctuate near the horizon, and if you restrict yourself just to the Rindler patch, those vacuum fluctuations look like things jumping in and jumping out and jumping in and jumping out, and there's a steady state. So if you plant yourself a certain distance from the horizon, what you will see is a steady state with an average number of particles in each little box, and they don't go away, they stay there. But actually what's happening, if you want to follow particle by particle, it's jumping out and it's falling in. It's jumping out and it's falling in. There's nothing hovering. And you don't have to find a model of things that hover above the horizon.
Well, this is not just for Stephen, but if we have no event horizon, does that mean we don't have an interior? Is there a description for the infalling observer?
Raphael was looking at me, but I don't have an answer.
So if you think about D-brane dynamics at finite n,
we can't hear you,
at
sorry.
finite n, even in the geometric regime, the horizon is not well defined, and then you can even go further and work at small lambda, small n, and what used to be the horizon, described by some dBi action, has become a much messier, dynamics that has replaced the horizon, but it's not, that nothing replaces it. It's just instead, in that context, particle production dynamics is what has replaced the causal propagation at strong coupling. So this is just a model for how things can vary as you go from strong coupling to weak coupling and from infinite n to finite n. I don't think you have to say that that there's no description of an infalling object. It's just a different description.
Yeah, I think the best way to think about this is to think about the concept of a stretched horizon. So there's a surface which has the topology of a time-like interval times a sphere, and that sphere has a radius that changes with time as the black hole evaporates. And there's a certain set of degrees of freedom associated with that system, and that number of degrees of freedom goes down with time after the black hole has formed, assuming you don't feed it, and so on. And then the real question is, if something which looks like a bunch of particles encounters that surface in space, is there a period, a finite period, of order the light crossing time of that surface for which those particles can behave more or less normally as we would expect them to in flat space? We know that eventually, long before the black hole evaporates, they don't behave normally. Something terrible happens. They equilibrate with the rest of the degrees of freedom, whatever they are, that make up this object. And so I think the real question is, what are the degrees of freedom that make up this object? And how many degrees of freedom do you need to describe particles interacting with this object inside? And whether they're affected by the interaction over a time scale of order the Schwarzschild radius.
I agree with almost everything you said, except for what you said was the real question. Because the AMPS argument holds no matter what the degrees of freedom are. It doesn't matter how we mock up, what's the underlying quantum gravity theory. As long as it reproduces these three things that we want to be true, there's a conflict. And so I think we have to address this issue. If we say there's no event horizon, does this mean that there's no interior, in which case there's a firewall?
I totally agree with what Tom said, that should be the picture. And I just backing up what Raphael said, the question is whether that picture can be consistent with the hypothesis, say, unitarity of quantum mechanics and so on. Because I'm saying it's not consistent. Whether you can consistently do what Tom said is that question.
Very briefly respond to this. The real question is, which of those assumptions do you want to give up? I believe the correct assumption to give up is that there's a notion of low energy field theory which is valid for answering this question. No, low energy field theory breaks down everywhere all the time.
That's not better.
Dude. Yeah. No, yeah, I just had a, so you when you said you wanted to take a time of order the Schwarzschild time, you really mean in the proper time of the particles that are falling in? But how do you really, I mean, from the point of view of the outside and the stretched horizon, how do you get a handle on that? I mean, from that point of view, I don't know, it takes it forever to get to the horizon.
There's a...
Okay, so I agree with that. I think the right way to think about that is in terms of quantum mechanics defined along time-like trajectories. And there's a question of how the time along that trajectory is actually related to the external time. And I'll talk about that in my talk. It would take too long to do it here.
Sorry, Daniel, just one.
One quick thing to just respond to Raphael's comment, that you said that if the effective field theory breaks down at the stretch horizon, then the horizon is a very special location. I don't think that's, of course, I think you know what you mean, but in one description, like from distant description, that's the special place where effective field theory breakdown does not mean that, yes, yes. Yeah, just to clarify, I know you know what, yeah, sorry.
Sorry, Daniel, just to answer your question, I think also...
I think the microphone was off. I don't know if you heard that, Stephen, but we just thank you, and we hope that you're enjoying the proceedings remotely and enjoying the continued trouble that you stirred up with your paper from 1976. So we'll break now, and Bill Unruh speaks at 11 o'clock. Stephen, there was also some recorded discussion while you were asking the question. We recorded some ongoing discussion related to your talk that will be on the web when your talk is posted.
Okay. Did you hear Stephen's last comment?
Would someone define the stretched horizon?
Hold on, Stephen is speaking.
Oh, sorry.
Did you hear Stephen's last comment?
I'm sorry?
Did you hear Stephen's last comment?
No, we missed it.
Would someone define the stretched horizon?
Who would like to define the stretched horizon? Lenny, it's been requested that someone...
I'm sorry. Look, I discussed these questions in this particular institution about 20 years ago, and no.
Okay, maybe Tom, he will give it a try.
Lenny taught me about 20 years ago what the stretched horizon was. I think of it as I said, as this time-like cylinder, which has a certain energy and has a certain number of degrees of freedom associated with it, and with which, once you interact with it, classically, it seems like you get lost forever. And really, we have to understand what happens to you in your own proper time and how long it takes for you to get lost.
And I think Tom neglected to mention that it's about a Planck distance outside the horizon, so it's where a dangled observer would feel the Planck temperature.
It looks like a green line if you get up close. If you get up, it's the green line. It's the green line. So that's our best attempt to define the stretched horizon. I never say that word. So, I guess if he chooses, can he follow Bill Unruh's talk live? Do we?
Yes.
He will. Okay.
Yeah, we have that. He has given him the URL. He just said that the time difference is difficult.
Thank you.
I think he said thank you.
Craig, turn it up.
Craig. Okay, we missed that last comment.
Stephen said thank you.
Thank you, and you're welcome. We hope you enjoy the rest of the meeting.
Did you hear? Can I just check you heard Stephen's middle comment? Where he said there were no. I say there are no event horizons. Did you hear that comment?
Yes, we heard that, and there was discussion of what it means. Lenny agreed with it, but then. Yes, there was some. We heard that, and there was some response to it.
We didn't quite hear everything, so we'll take a look at the video.
Thank you, and please, Stephen, if you have additional comments, questions at any time offline, you can email them or anything, and they'll be relayed to the group, and we can discuss further. Thank you.
Thanks. Okay.